Astronomers are always talking about rare cosmic events like eclipses and comets that appear every 76 years. But what if we were to tell you that there's an event even more rare that is happening right under our noses? You see, today rather than looking at the giant balls of gas that make up our night sky, we're going to take a look at the microscopic world and see how two life forms came together in a once-in-a-lifetime event. Welcome to Atomic Stories. The first time two life forms merged was a recent 2.2 billion years ago, when an archaea, one of the ancient cell types, swallowed a bacterium capable of respiration to become one of the important organelles that eukaryotes have. Which one, you may ask? Well, you may know it as the powerhouse of the cell, otherwise known as the mitochondria, but us biochemists know it as the ATP bioreactor. Moving on in time, and we get a more recent example of life merging. Just 1.6 billion years ago, a cyanobacteria was engulfed by another eukaryote, resulting in the formation of the chloroplast. So the last time merging of two cellular species occurred, plants emerged. Doesn't it feel like it was just yesterday? And now we skip forward to today, where recently an algae has been discovered to have engulfed a cyanobacteria, which is a bacteria that can make up energy using photosynthesis. And together they formed a new organelle, which was named the Nitroplast. And more about what it does later. For now, just know this. Sometimes the coolest cosmic events aren't in space, they're happening right here on Earth. Think of two entities that come together and can do what neither of them can do alone. This is endosymbiosis. An example of endosymbiosis is when one organism lives within another, so closely that they eventually become inseparable, functioning as one. Gradually, the internalized organism evolves to photosynthesize latent energy, fix nitrogen into a bioavailable form, or synthesize essential nutrients not otherwise available to the host. This process has been at the core of some of the most important developments in life's history. Imagine a scenario where our ability to hear evolved from a symbiotic relationship with an external organism. Picture a small, shell-like creature living on rocks by the sea, capable of detecting sound vibrations in the water. Early humans, lacking the ability to hear, rely on other senses to navigate their environment. One day, a curious individual, while exploring the shoreline, picks up this creature and places it near their head. To everyone's astonishment, the creature attaches itself to the ear and starts interpreting vibrations from the air, allowing the person to hear for the first time. Over generations, this behavior becomes common practice, and eventually, the creature evolves to integrate seamlessly into the human body, becoming a fundamental organ for hearing. Well, rather than a human and shell-like creature merging together, in the real world, an algae and a cyanobacteria merged together and evolved the Nitroplast. The cellular structure specializes in nitrogen fixation, which is a process where atmospheric nitrogen, N2, is converted into ammonia, NH3. And the thing about ammonia is that it is a crucial component for building proteins in DNA. This conversion is also no small feat. Nitrogen molecules are extremely stable due to their strong triple bonds, making them resistant to chemical reactions. Through a series of enzyme-catalyzed steps, specifically involving the enzyme nitrogenase, these bonds are broken, allowing nitrogen to combine with hydrogen to form ammonia. What sets the Nitroplast apart is that this transformative process happens directly within the host organism, meaning that the host gets direct access to ammonia, and as we mentioned, this is a key resource. Why does this matter? Well, organisms equipped with Nitroplast could come to dominate nitrogen-depleted environments, potentially leading to the emergence of new species and shifts in ecological balance. The Nitroplast could disrupt entire ecosystems by fundamentally altering the nitrogen cycle. Such changes might lead to unforeseen consequences, affecting not just the host organism, but also the broader ecological balance. But it can also be helpful. Imagine if crops required minimal or no fertilizer because they can fix their own nitrogen using the Nitroplast, making crop harvesting cheaper and more sustainable. And that's not all, as it could also have a lot of potential in biotechnological applications. In addition to having an impact on agriculture, their ability to produce ammonia is particularly important for biofuel production, as ammonia serves as a carbon-free energy carrier with a high energy density. This characteristic makes it especially valuable in power generation and as a storage medium for renewable energy. Hydrogen, while renowned for its clean energy potential, presents challenges in terms of storage and transportation due to its low density and the complexities involved in handling it. Ammonia, however, offers an efficient and safer alternative as it can store hydrogen more effectively. Ammonia can be transported using existing infrastructure and later decomposed to release hydrogen precisely when and where it's needed. That's the end of the video, and we really hope you enjoyed learning a bit about the mechanisms of life. If you enjoyed our video, feel free to give us a like and subscribe and share it with your friends and family. We are a small channel, and all feedback is welcome to help us improve and make videos that you enjoy more. Thank you very much for watching. Bye bye.